1, 2. Good morning. The next talk will be about unlocking File Vault, the encrypted file system in Mac OS X computers. All of you Mac users probably know this. Besides the fact that they claim to use AES with 128-bit, it was so far not really sure what was behind it, how it worked. Now Jacob Appelbaum and Ralf Philipp Weinmann had a look into that, and they will present their findings and what they found out, how it works, and what is really done there. Please welcome them and have fun with that talk. Thank you.
So just to start off, we have a wonderful guest performer here who's going to perform a song for us. This is Johannes from Monochrome.
It's so embarrassing, I tell you.
He's wearing an Amish hat that's made in China, but he actually bought it in the Amish village in America. Yeah. So he's going to play us a song just to sort of set the mood for our talk.
Okay. Yeah, the problem was I was really drunk yesterday at 2 o'clock in the morning, and Jake Appelbaum came and said, "Come on, I have a talk at 11:30 tomorrow in the morning, and all the people, they have to, like, we have to wake them up. We have to do a little performance for them that you really can, like, dig into cryptography, you know, and stuff like that." So he said, "Okay, we need a song about Apple." And I said, "Okay, I drank 7 Club Mate, so I can't drink any. I can't sleep anyway. So I can think about doing a song, and I'm really proud it's a copyright infringement. And actually, I don't even use an Apple, but I thought maybe trying to write a love song for Apple. So that's what came out, and I hope you somehow can enjoy it. But anyways, it will be on the internet soon, whatever. Okay, so I think I have to switch to my media player. Long intro. So close, no matter how far. Just how far. Couldn't be much more from the heart. Forever trusting who we are. Oh fuck, I love Apple. Never opened myself this way. Life is ours, we live it our way. All these words I don't just say. It's different, it's Apple. Trust I seek and I find in you. Every day for us something new. Open mind for a different view. A corporation called Apple. So close, no matter how far, it's soon over. It couldn't be much more from the heart. Forever trusting who we are. Oh my God, oh my God, oh my God, oh my God, Apple. Thank you very much.
Something only Monochrome could come up with. Thank you. So today we're going to talk about File Vault, and I think that the results should be interesting for everyone here. I'm interested to know, though, everyone in the audience, if you use FileVault or if you have a Mac or something along those lines, maybe a different disk crypto program, could you raise your hand?
Okay.
So we're going to talk about what FileVault is, and we're going to talk about problems that other people have found and that we found with FileVault. We're going to talk about reverse engineering on OS X. We're going to talk about like the non-free disk image framework. We're going to talk about free implementation that we're going to release. We're also going to talk about some of the other oddities of Mac OS X. And we have a special guest hacker here. This is Hikari. Very amazing guy. He's one of the founders of Torcon, and we were fortunate to have him here. And he put together his contribution in about, what did you say, about 45 minutes or an hour or something to get it working, and then not including up until 5 minutes ago. All right. So my motivation and Ralph's motivation for this was that we're pretty much interested in disk crypto. Personally, if you saw my talk last year, you know that I have a sort of like passion for data being secure. We also wanted to protect against theft, so we're really interested in the native disk encryption that comes with OS X. And everybody uses laptops. I mean, most of the people here using FileVault, I assume you have laptops. But it's undocumented, and we wanted to know if it was secure and how it works, and Apple claims, you know, unbreakable, trillions of years, and all that stuff. So on the marketing side, they say, FileVault secures your home directory by encrypting its entire contents using the advanced encryption standard with 128-bit keys. This high-performance algorithm automatically encrypts and decrypts in real time, so you don't even know it's happening. Yes, FileVault, increase security for your computer. But we actually do want to know what's happening inside. That seems like a good thing. So the internals are not well documented. You can look at the man page for HDI util. The disk image framework is private. You have no source, no headers. It needs to be reversed. And the kernel module stuff is not open sourced. So
what we looked at first was the only documentation around is for the HDI util. This is very good because HDI util has a command that allows you to list all the plugins. Disk images is like a very modular framework, so it consists of different plugins. And so far, the only third-party plugin known that was developed outside of Apple's is a plugin for virtual PC images. Now, there's a front end and a back end. The front end is the HDI util program. The back end consists of basically a kernel module that's handling the attach of disk images and a couple of helper programs such as Disk Images Helper, and HDI ejectd. Now, when you you have to go to the next slide. This disk image framework has several backing stores. Backing stores are basically the containers that hold your data. And there's like a CBSD backing store, which is just for normal files that hold data. Then there's like a CRAM backing store for RAM disks and different other things, like a CURL backing store, so we can have like the image on like an HTTP server or HTTPS server. And another thing is you have encodings, and what we will look at mostly in this talk is the C encrypted encoding. That's basically the encoding that does the AES 128 and the other cryptographic stuff. And this C encrypted encoding is the heart of FileVault, basically. The other thing is that FileVault does not allocate like a static amount of space on your hard drive, but it has a sparse disk image that grows. Now, there's different types of disk images that are supported by the disk images framework. There are like shadowed disk images where you only write back the changes to one image and you have a master image in another container. Then there are compressed images and, and then there are sparse images. Now, to get to the crypto details, when you have like the C encrypted encoding, which is basically the outer layer of a FileVault image, like you have an inner layer, which is the sparse image, and you have the outer layer that's produced by the C-encrypted encoding. Then all of the blocks get encrypted in 4 kilobyte chunks using AES-128. And that is in CBC mode. Now, the IV for each of these chunks is generated using HMAC SHA-1, and the key for there's a key that's used for generating these IVs, and that's the HMAC key. I'll go into where these keys come from in a second, but for now it's just an HMAC key. And basically what you do is you have this HMAC key and you prepend the chunk number to the HMAC key and then apply the HMAC. And that truncated to the first 128 bits gives you the IV for this chunk. Now the keys are randomly generated when you create your file vault, and then they are wrapped in the header of an image. Now this header is, well, it's kind of a misnomer because sometimes it's a header that's in the old versions, like there's version 1 and version 2 of the metadata format, and in version 1 it was actually at the beginning of the disk image, and in version 2 it's at, sorry, the other way around. In version 1 of the format, it was at the end of the disk image. In version 2, it's at the beginning of the disk image. Now, what's interesting is that the wrapping of these AES keys is done using triple DES for some reason. So, in fact, I mean, it's kind of cheating because now the security doesn't only depend on AES, but if either AES or triple DES fails, you're screwed, right? Okay, and what they did when they went to version 2 of the metadata format, which was, I think, in Panther, is they introduced an option for having an additional asymmetrically encoded header. And what this is good for is for a recovery feature. I'll go into that a little later. First, let's look at the normal way you unlock your file image again. So the passphrase for your file image is your normal login password. So if your login password is wrong, is weak, your file is used as well. What they use for deriving the key for unwrapping the other keys is something called PBKDF2. That's a very standard algorithm. It's in the RSA PK CS5 series of algorithms. And they use this algorithm, which is parameterized with 1,000 iterations, which is, well, it's kind of low. But you don't want to wait forever for your disk image to attach, so that's probably why they choose a low number of iterations. And what's interesting as well is that most of the crypto parts are actually implemented in something called CDSA. That's the common. Sorry, it's an architecture for cryptography that was developed by Intel, and this architecture actually is open source, and it's modular as well. So it's like bloat. I mean, there's this huge meta framework, and then you have providers sitting in this meta framework, and there's one Apple CSP provider. And this is also what makes like porting like the reverse engineered implementation kind of hard, because then you have to port all of the other crap as well. I mean, CDSA exists on Linux as well, but you'd have to port the Apple CDSA provider. So what we decided to do for the free implementation was we did away with all of the CDSA stuff, and we used OpenSSL instead, because that's much leaner. For performance reasons, Disk Images has its own AES implementation. However, it pulls in the SHA-1 from an OpenSSL lib. So this is kind of inconsequential as well, because I mean they have CDSA, but some stuff comes from other parts. And the wrapping that they've